Given a target array of positive integers. Start from an array of the same length filled with ones. Each step replaces one element with the sum of the whole array. Return true if you can reach target exactly, otherwise false. Example 1 with target 935. Start from 3 ones. Pick index 1 and replace it with some 3. Pick index 2 and replace it with some 5. Pick index 0 and replace it with some 9. We reach the target array. Output is true. Example 2 with target 1112. For ones are easy to build, but 2 can never appear as a sum of ones. Output is false. If we try to solve this problem by starting at our base array of all ones and building forward, we are instantly blindfolded. At every single step, we have to guess which index was updated next. This creates an exponentially growing tree of choices that quickly floods our screen with chaotic paths. We need to flip our perspective entirely. Instead of guessing forward, let's run the movie in reverse. Look closely at our final destination, 9, 3, and 5. Because every forward step requires replacing a number with the sum of the entire array, the largest number on the board must be the one that was just created. This means there is no guessing game. There is exactly one unique path backward in time, and it always begins with the maximum element. To figure out what this 9 looked like before it was transformed, we have to isolate its historical footprint. First, we compute the total weight of our current array, which sums to 17. If we subtract our maximum element from that total, we get 8. This 8 is incredibly important. It represents the absolute, unchangeable sum of all the other elements on the board at this exact moment in history. Since the current maximum was built by adding the rest of the array to its own previous value, we can reverse that addition perfectly. We take our max value of 9, subtract the historical footprint of the field, which is 8, and we unlock its original value, 1. We drop this 1 back into the array, successfully stepping 1 frame backward in history. Our engine shifts focus to our new maximum, 5. The row now weighs 9 in total, while the rest of the field sums to 4. Subtracting 4 from 5 leaves us with 1. But what if that maximum card was an incredibly massive number like 1000? Subtracting 4 over and over again in a slow loop would completely destroy our performance. To stay perfectly efficient, we use a remainder reduction. Dividing our maximum by the field sum lets us compute thousands of repetitive subtractions instantly in a single leap. We repeat this exact cycle, identify the maximum, peek at the top of a max heap, isolate the field, and apply our remainder reduction. Step by step, the numbers melt backward until our array perfectly converges into our baseline of all ones. Because we successfully reached our true origin state with 0 logical roadblocks, we have proven that this target array is completely valid. We begin our solution by feeding our target elements into a max priority heap structure. This structure ensures that whichever number is currently the largest instantly floats to the top of our operational scale. Concurrently, we accumulate all elements into a running sum variable, giving us a baseline world weight of 17. We kick off our backward reduction loop, which runs as long as the largest number on our board is greater than 1. We pop off the current maximum element, which is 9, and subtract it from our total world sum. This isolates our field weight. The other remaining elements combined have a total weight of 8. We execute remainder reduction. Instead of slow linear subtractions, we modulo the maximum by the rest of the sum. 9 mod 8 leaves a remainder of 1. That single step reveals what this slot looked like 1 frame earlier in history. We push the restored value 1 back into the priority heap for the next round. Then we update total sum, subtract the old maximum 9 and add the new previous value 1, bringing our world weight down to 9. The engine repeats the same cycle. 5 peels to 1, then 3 peels to 1, until every card on our stage reads 1. The maximum pulled from our heap is no longer greater than 1. We return true, confirming that target 935 is reachable. In code, we handle this before the loop. If the target has only one element, it must already be 1. A lone 5 returns false. A lone 1 returns true. Inside the loop, if the maximum is not strictly greater than the rest of the field, the timeline is broken. Problem example 2 fails here, 2 is not greater than 3. When the rest of the field sums to exactly 1, any large maximum is valid, we return true immediately without modulo. That is why 1 and 1 billion is easy. When modulo would zero out a card, we remap to the rest sum instead. Our origin floor is 1, not 0. N is the length of target. Time is O of n log n, each backward peel extracts the max and reinserts the peeled value, and each heap operation costs log n, we perform at most O of n such rounds. Modulo replaces many linear subtractions with one step per round. Space is O of n for the max heap plus O of 1 for the running total. Function is possible takes the target array we must reverse build from all ones. If the target has only one element, that lone value must already be 1, otherwise return false. Feed every target value into a max priority heap, same as build max heap in the solution. Accumulate all elements into total sum, our running world weight. The backward loop runs while the heap peak is greater than 1, matching the solution snippet. Pop off the current maximum from the heap. Subtract it from total sum to isolate the rest of the field. When the rest of the field sums to exactly 1, any large maximum is valid, return true immediately. If the maximum is not strictly greater than the rest, the timeline is broken, return false. One modulo step reveals what that slot looked like one frame earlier. When modulo would zero out the card, remap to the rest sum instead, our floor is 1, not 0. If the peeled value would not shrink the maximum, the reduction cannot continue, return false. Push the restored value back into the priority heap. Update total sum, subtract the old max and add the previous value. When the heap peak is no longer greater than 1, return true.